So I'll go ahead and get started. Oops. I have a lot to go over today. I'm going to go through basically the entire first section that we did so far. So stay with me. Just unmute yourself or put it in the chat if you have a question as I'm going through all this. But I'm going to go through beta elimination, which is what this whole section is about, just the basics of that. Dehydrohalogenation, E1 and E2 mechanisms, and their regio and stereochemistry, and then acid catalyzed dehydration of alcohols, and then carbocation rearrangement. So again, just stop me if you have questions as I go through this. So again, this whole section was on beta elimination, which is a type of reaction where a leaving group in a hydrogen from an adjacent carbon is eliminated to form a double bond. So it forms, your product is an alkene. So beta elimination requires a good leaving group and a base, and typically you'll either use an alkoxide, which is, remember this, okay, that's an alkoxide or hydroxide. So those are the bases you'll typically use. And it requires heating because bonds would be broken. So to break bonds, you need to input energy, and that energy will come from heating. So down here I have like kind of a diagram to show this, but here, let me get the pointer. So right here I have the alpha carbon. And the alpha carbon is the carbon that's directly connected to the functional group, in this case, which is the chloro group. So it's our functional group, and your alpha carbon is highlighted in green, is the carbon that's directly connected to that functional group. And then your beta carbons are the ones that are connected to the alpha carbon. Okay, this is the beta symbol right here, and this is alpha symbol. So, and the hydrogens, which are highlighted in blue, are beta hydrogens, which are the hydrogens that are connected to the beta carbons. Okay, so those are the hydrogens that will be eliminated. Okay, any questions so far? Okay, so the first type of beta elimination reaction we learned about was dehydrohalogenation. Okay, and that is just a beta elimination where the leaving group is a halogen, so either chlorine, bromine, or iodine. And again, H, and so a hydrogen and the halogen is eliminated. Okay, so the general reaction, you have a halo alkane. Okay, so you have X, a halo group on your alkane. You need a strong base, so again, it's typically an alkoxide or hydroxide. And your product is an alkene, BH, so the base combines with the hydrogen, and then this halo group comes off as an anion. Okay. So dehydrohalogenation and other beta elimination reactions can happen through two different mechanism pathways. The first one is E1 reactions. So happens in two steps via carbocation. So just like SN1 reactions, if you remember, SN1 is two steps, SN2 is one. So just the same thing. E1 reactions happen in two steps, and they happen via a carbocation. E1 reactions can occur with secondary and tertiary substrates. And remember, that is because primary carbocations cannot be actually formed. So secondary and tertiary carbocations are the only ones that can be actually formed in a reaction. In E1 reactions, the rate determining step involves only the substrate. So hence E1, the 1 means that the rate of the reaction is first order, which means that it only involves one molecule. And for E1 reactions, you can use a lower concentration of a base, so it doesn't have to be as strong as the E2 reactions. Okay. So in E2 reactions, it happens in one step, so just similar to SN2. It can occur with all substrates, so even tertiary. And the rate determining step involves both the base and the substrate. So the 2 in E2 reactions just means that the rate is second order. So it involves 2 molecules at the rate determining step. Okay. And E2 reactions will require a higher concentration of a strong base. And it requires the leaving group and the beta hydrogen that are being eliminated to be anti-coplanar, which means that they're in the same plane, but they're opposite each other. Okay. So it's kind of similar to SN1 and SN2, but it's not as easy to tell which one will occur as SN1 and SN2. Okay. So here I have an example of an E1 reaction. So this here, this chlorine is connected to this hydrogen, it's connected to 2 other hydrogens. So this is a secondary substrate. Okay, and I have a hydroxide here, it's a strong base. So my product here, this chlorine will be eliminated as well as one of these hydrogens. It doesn't matter which one since they're equivalent, and will form a double bond in its place. This should have a hydrogen here, my bad. Okay, so that will be eliminated and there'll be a double bond in its place, as well as water will be formed and a chlorine anion. Okay, so in E1 reactions, the first step is the leaving group comes off. So this bond, this C chlorine bond will break, and these bonding electrons will go to the chlorine, and that will come off. So we lose chlorine here. Okay, and we have a carbocation formed. And this process is the slow step. It's the rate determining step. As you can see here, it only involves the substrate here. And we'll get to this more later on, but as of right now, can anyone tell me if this carbocation can rearrange at all? Let's try, shall we? I missed a hydrogen here, by the way, I'm sorry. There should be a hydrogen here and here. Okay, so if I try to rearrange this carbocation, okay, I can't move this methyl group anywhere because that would just give me the exact same thing. Okay, if I try to move like one of these hydrogens here, if I move this hydrogen to this carbon, positive charge will shift to this carbon, and that would be a primary carbocation. So that won't help us at all. And same thing on the other side. So this won't rearrange because there's no possibility for a more stable carbocation. Okay, so now that I have the carbocation formed, you're okay, Caitlin. Like I said, we will get there. I was just asking, but I'll go into more detail later. So after we have the carbocation formed, base will come in. It will take either one of the beta hydrogens. Okay, so we have 2 beta carbons here, right? We have this beta carbon, this beta carbon, which are both connected to the alpha carbon. Okay, so I can either take a hydrogen from this carbon or this one. In this case, it doesn't matter because it's a symmetrical, they're equivalent, it'll give you the same product, okay? So it doesn't matter which one you take here. So the hydroxide, come and take this hydrogen here, this CH bond will break, and those bonding electrons will go to the CC bond domain to form your double bond, and it will neutralize that positive charge. So here is your product there. The water comes from the hydroxide taking the hydrogen here, and then this chlorine came off back here. Okay. that make sense? Okay. So E2 reactions are similar, but like I said, they do not involve carbocations, and it happens in one step. Okay, so this, I have my chlorine here, which will be my leaving group. It's connected to this carbon, which is connected to one other carbon. Let's see, I don't remember. Yes, I did. My bad. I'm sorry. I left a hydrogen off all these. Oops. But yeah, all of those should have another carbon. All your carbons should have 4 bonds. Okay, thank you, Carol. Okay, so anyway, here's my chlorine here, which will be my leaving group. It's connected to this carbon, which is connected to one other carbon. So this is a primary substrate. Okay, primary substrates can only have E2 reactions. And remember, the heating for primary substrates is way, way, way high. So they don't do them very often. It's not a very favorable reaction because of the high heating, but just for education's sake, we'll go through this. But just know that the heating it's 180 degrees. It's very high. So it requires a lot of energy. Okay, so again, this is the primary substrate. We have our strong base, and this will need to be more concentrated than the E1 reactions. In our product, we have this chlorine taken off, and this hydrogen also eliminated, and a double bond will be formed in between here. Okay, and then also water and a chlorine anion will be formed. Okay, so in E2 reactions, it is a requirement that your leaving group and your beta hydrogen are anti-coplanar. Okay, which means these are all connected by a line, which means they're in the same plane, but they're opposite each other. Okay, so that's the requirement for E2 reactions. And this is already anti-coplanar, so we can go ahead and proceed with the reaction. Yes?
Could you ask them whether they can see your plus sign anymore?
This is the pen, so I don't think they can see it, but I think they can see. You can see this pointer, right? Here. My people and collaborate.
You ask them.
Yes, okay. Yeah, they can see this, but
Okay.
So I'll try to use this instead of the pen, sorry. Okay. So like I said, E2 reactions happen in one step instead of two, so there's no carbocations. Okay. So your hydroxide is going to attack your beta hydrogen here. At the same time, this CH bond will break. These bonding electrons will go to the CC bond domain to form your double bond. And then at the same time, your leaving group will come off. Okay, so that all happens in one step. And as all this is happening, these groups are shifting down, and these are shifting up. See here I have the double bond formed, and again, those shifted down, and these came up. So that's a nice symmetrical molecule. And then water formed from hydroxide taking that beta hydrogen, and the chlorine came off as an anion. Okay, you all good with that one? Okay. So now into regiochemistry and stereochemistry. So regiochemistry, if you remember, is studying the distribution of different structural isomers, and stereochemistry is studying the distribution of stereoisomers. Okay, so for E1 reactions, both the regiochemistry and stereochemistry is determined by the stability of the carbocation and the product. Okay, so there's no kinetic control in E1 reactions. It's only under thermodynamic control, which just means that the major product is only determined by how stable the product is. Okay, so I have an example here. Can go through. So here, chlorine here will be our leaving group. It's connected to this alpha carbon, and these two are my beta carbons. Okay, so this is secondary substrate. That was a terrible two. going to react with hydroxide, and here you're going to form two different products because this substrate is unsymmetrical, meaning that both of the beta hydrogens are not equivalent. So eliminating either one of the beta hydrogens will give you a different product. Okay, so do we remember which one out of these will be more stable? Cool. Okay, so the second one, this bottom one here, is going to be more stable because if you remember, a alkene is more stable the less hydrogen it has around the double bond. Okay, because alkyl groups stabilize a double bond. Okay, so up here I have three hydrogens, 1, 2, 3, three hydrogens around this double bond. Here I only have 2. Okay, so this will be more stable because it has less hydrogen and therefore more alkyl groups around double bond. So we can go ahead and go through that mechanism. Okay, so first step, again, is this carbon-chlorine bond will break, form a carbocation. Okay, and then we have our hydroxide. And this hydroxide can either take one of these hydrogens or one of these, right, the secondary carbocation. And again, we'll get into this later, but again, this cannot rearrange because if I moved any of these hydrogens, it wouldn't give me anything above a secondary carbocation. Okay, but we'll get into that more later. So this hydroxide can either take beta hydrogen here or here. Like we already said, the double bond here will make the more stable product. So the hydroxide will more favorably take one of these hydrogens instead of this one because that will give me the double bond in the middle here. Okay. So okay. Okay, so that is a more stable product. Okay, and if the hydroxide took one of these hydrogens instead, it would give me this product. Okay, so that's the regiochemistry, is just determined by the stability of the product. So just remember that the more hydrogen around the double bond, the less stable it will be because alpha groups will stabilize your double bond. Okay, so stereochemistry, it's the same thing. It's also determined by stability of the product. So we do have stereochemistry in this reaction because we can have cis and trans isomers, okay? And remember, you can tell if you have cis-trans isomerism if you have two different groups on each of the doubly bonded carbons, okay? So here, this carbon has a hydrogen and a methyl group. This one also has a hydrogen and a methyl group, okay? So you know if both of those doubly bonded carbons have two different groups on them, then you can have stereoisomers, okay? So I can either have cis or trans. Okay, remember that trans isomers are more stable because these alkyl groups are as far away from each other as possible. Okay, so that's giving me the most amount of room between all these electron clouds. So there's the least amount of repulsion as possible. Okay, and if these two groups were not the same on either side, but they're still different, if that makes sense. So if both of the carbons do not have the same groups, but both of them still have two different groups on them, you can still have stereoisomers. You'll just have to use E and Z instead of cis and trans. Okay. Okay, so E2 reactions is a little bit more complicated for regeo and stereochemistry. So the regiochemistry for E2 reactions is determined by the stability of the product and the bulkiness of the base. Okay, so the bulkiness of the base is basically just how big the base is. So really the only bulky base you'll need to know is T-butoxide, okay, which is an alkoxide with a tertiary butyl group on it. And then your non-bulky bases, so your small ones, are hydroxide, methoxide, ethoxide. Okay. So regiochemistry has both kinetic and thermodynamic control. Okay. So depending on the type of base you use, your major product would either be determined by how stable your product is or how fast it's formed. And there's stereochemistry is for E2 reactions determined by the structure of the substrate. So it has to be anticoplanar, or you cannot have an E2 reaction. Okay, so the same substrate here, but two different bases. Okay, so this here is T-butoxide. Like I said, it's an alkoxide with a tertiary butyl group on it. So if I try to okay, so the major product for this reaction is this one here, which is less stable. We talked about in the last example, which is less stable than this one. Okay, so, and that is because if I try to get this, so this is, I'll try to make sure you can see this here. Okay, so this is T-butoxide, right? And this is our substrate. Okay, so the more stable product would be formed if my T-butoxide took this hydrogen here, okay? But if I try to do that, you see how this group is hitting this group, and it's just, there's going to be a lot of repulsion, okay? So that's not very favorable for this to take this hydrogen, even though that would be more stable, okay? So instead of this big giant base trying to get in here, it's going to come over here and take this hydrogen, okay? Which is a lot easier because there's no groups around here that will cause repulsion, okay? So, like I said, this base will actually take, yes, I'm drawing now. So this base will actually take this hydrogen, okay, instead of this one over here, because it's a lot easier to get over here. There's much less steric hindrance and repulsion from all those electron clouds, okay? So this base will take this hydrogen here. Those bonding electrons will go in between there to form the double bond. And then this chlorine will come off at the same time. Okay, and this will be your major product here. Okay, even though it's less stable, because this is under kinetic control, which means that the major product is determined by how fast the reaction goes. So this, the T-butoxide taking that first hydrogen, this reaction, this mechanism will be a lot faster than it trying to take that third carbon's hydrogen. Okay, so because it's happening faster, that will be the major product. Okay, so this is under kinetic control, and this is a Hofmann reaction. Okay. Okay, so alternatively, if I use a non-bulky base like hydroxide here with the same substrate, okay, I'll actually get the more stable product because because there's no steric hindrance because this is so small. Okay, so this hydroxide will take this hydrogen from that third carbon, and I'll get a more stable product. Okay, because there's no steric hindrance, or there's minimal steric hindrance at least. Okay, so the top reaction is under kinetic control. This is under thermodynamic control, which means that the major product is determined by the stability of that product. Okay, and this is Zaitsev reaction. Okay, so Hoffman reactions are under kinetic control. Zaitsev are under thermodynamic control. Okay, does that make sense? Okay, any questions so far? Okay, so that's not the right product for that, but we'll come back. Okay, so stereochemistry for E2 reactions is determined by the structure of the substrate. Okay, so remember the hydrogen being eliminated and the leaving group have to be anti-coplanar. Okay, so that means they're in the same plane, but they're opposite each other. Okay, so right here, they're not anti-coplanar. Okay. So this compound here is in eclipsed conformation, and we need it in staggered conformation, okay? So I'll show you this here. Okay, so these are just hydrogens, but so I have this, pretend this is a hydrogen, this is bromine, okay, they're in the same plane, and then I have an ethyl group, I have a hydrogen in front of the plane, or that's in the back, yeah, this is the ethyl group, and this is the hydrogen in the back of the plane, and then I have hydrogen and methyl group in the front of the plane, okay? So if you remember in Newman projections, do this thing here, okay? So this would be this middle carbon here, okay? So the angle here, okay, these are 120 degrees apart, okay? If I'm looking at it right from the front this way, okay? So this is an eclipse formation. Okay, if I want it in staggered, I'm going to rotate it 60 degrees, okay? And that will put it in staggered conformation, okay? So that's exactly what I'm going to do here. Is because this is not anti-coplanar, this is not in staggered, I'm going to rotate that left carbon 60 degrees, okay? Because I want this hydrogen that's in the back, I want it rotated in the plane, okay? So when I do that, okay, so I have this hydrogen, or this hydrogen in the back, this methyl group in the front. I want this hydrogen in the plane, so I'm going to shift this just like this. Okay, so now this is in the plane. This methyl group is still in the front. Okay, and now this hydrogen is in the back. Okay. Okay. Does that make sense, everybody? I know it's a little complicated, but our goal here is just to get those anticoplanar, okay? So now, as you can see, this hydrogen is connected to this carbon, to bromine, all in just single lines. So that means they're in the same plane, but they're opposite each other. So now we can proceed with the reaction, okay? Okay, so now my hydrogen is going to come in, which will take this hydrogen here. This will go in between the carbons to make that double bond, and then this bromine will come off. Okay, so this will be our product here. I know it's messy, but hopefully that made sense. Okay, so just the big takeaway from that is you need to have your hydrogen and your leaving group anticoplanar. Okay, so the next thing we went over was acid catalyzed dehydration of alcohols, which is another type of beta elimination. Okay, so this is where water is eliminated from an alcohol, and that forms an alkene. So secondary, tertiary alcohols follow an E1 mechanism, and then primary alcohols follow E2. Heating is still required for all of them, and for dehydration of alcohols, you need an acid to protonate this OH group to convert it to a good leaving group, because you need a good leaving group to have an elimination reaction. Okay, so the general reaction here is you have an alcohol, you need the acid to catalyze, and you need to heat. This water molecule will come off, and then you'll have a double bond formed in its place. Okay, so an example here of E1 dehydration, and you've done this reaction before in last semester, so try to remember that. So our first step is to protonate, okay, this OH group, because this OH is not a good leaving group. Okay, so it will not come off easily. Okay, so I'm going to protonate with that sulfuric acid. So that OH group will take that hydrogen, this bond will break, and now I have water here. Okay, so now we can proceed with the elimination reaction. So this good leaving group will then come off, so this carbon-oxygen bond will break, that water will come off. Okay, and then we'll form a carbocation. Okay, and here I again have two beta hydrogens or beta carbons, but they're equivalent, so it doesn't matter which hydrogen I take. Okay, so, and in E1 reactions, you can actually use, or dehydration reactions at least, you can actually use water to take that hydrogen, since you don't need as strong of a base for E1 reactions. So this water can take that hydrogen off. And these bonding electrons will go here to neutralize that positive charge and form the double bond. Okay, and you'll have hydronium, which happens when you have an acid in water. Okay, does that make sense? You have done these reactions so far, or before in the last semester, so this should be a little bit familiar at least. Okay, and then E2 similar. So this is a primary alcohol, which can only have E2 reactions for dehydration. Okay. So same thing, our first step is we need to protonate this OH group. Okay, so that those lone pairs from oxygen will go to this hydrogen to form another OH bond. Those bonding electrons will go to the oxygen to form an anion. Okay, so like I said, we have an anion here. Okay, so this anion will take the adjacent carbon's hydrogen, the beta hydrogen. These bonding electrons will go in between here to form that double bond, and at the same time, the water will come off. Okay, so that all happens in one step. Okay. And you can use the anion here because since this is E2, you need a bit of a stronger base. So this has a negative charge, so it'll be a bit stronger. The water itself is not strong enough to take off the hydrogen, and it also hasn't come off yet, so you can't use the water. Okay, everyone good with that? Okay. So last thing, if everyone's still with me, carbocation rearrangement. So this happens in both SN1 and E1 reactions. So if there's a possibility to make a more stable carbocation, it will happen spontaneously, okay? So methyl groups and hydride ions can shift to adjacent carbons if it will form a more stable carbocation, okay? So you always have to pay attention to if that can happen when you have carbocations formed, okay? So I have an example of each here. Can't see that. That's okay. Okay, so here's my substrate here. I have chlorine here attached to this carbon. It's a secondary substrate, okay? And then I have two methyl groups here. So first step is that chlorine will come off to form a carbocation. This is E1. Okay, so now I have a carbocation formed here, and this is secondary carbocation, right? Because this positive charge is on this carbon, which is connected to two other carbons, okay? But I have two methyl groups. I have two methyl groups up here, okay? So I can move one of these methyl groups to this carbon here, okay? Which will make this carbon here have 4 bonds because there's a hydrogen here. Don't forget that. There is a hydrogen here, okay? So if I move one of these methyl groups to this carbon here, this carbon will have 4 bonds, and this one will now have 3. So this positive charge will also shift to that carbon, okay? And that will give me a tertiary carbocation. Okay, so now the positive charge is on that carbon instead. And I still have this hydrogen here, okay? So I went from a secondary to a tertiary carbocation, which is more stable, okay? So you'll have to pay attention to if anything can move to make a more stable carbocation, it will, okay? So just be sure to pay attention to that and try all of your options. So now reaction can proceed. Again, this hydrogen or this hydroxide will take that hydrogen. Those bonding electrons will go here to form the double bond. Okay. So now this is my product. Okay. Which would be more stable than my unrearranged product, which would have double bond with a hydrogen on it. And this has no hydrogen. Okay. So that is a more stable product because of that rearrangement. Okay. Does that make sense? Stop me if you have any questions again. So this one, 3 bonds are where? Okay, so carbocation rearrangement can happen anywhere there's a carbocation.
Have you seen CoreQuest?
Yeah. So E1 and SN1 reactions occur via carbocations, so it can happen with both of those. And the 3 bonds on, I'm assuming you're meaning, I don't remember which one. Okay, so are you talking about on this carbon here with the positive charge? Okay. Yeah, so this carbon here, it's connected to this carbon and this carbon, so there's 2 bonds, and then it also has a hydrogen on it. Okay? Does that make sense? Yeah, so I didn't include it here, but all of these carbons on the ring have 2 hydrogens unless they have something else on them, okay? Because all of these carbons have to have 4 bonds. Okay, so that carbon always had a hydrogen on it. So that has 1, 2, 3 bonds. And then when I rearrange, this carbon here is connected to this one, and also this one. Or sorry, this one, and this one. So that one also has 3 bonds, which forms that positive charge. Okay. Okay. And now this one. So again, first step, that chlorine will come off, which will form a carbocation. Oh my goodness, I did it again. I'm so sorry. I keep forgetting my hydrogens. Okay. So this chlorine came off, and now I have this carbocation here, which is secondary, right? Okay. So we need to check if it can rearrange, right? So if I moved this methyl group to this carbon, okay, this positive charge would shift to this carbon, and that would give me another primary carbocation. So that would not help me at all. So my other option is I have a hydrogen on this carbon, okay? So if I move this hydrogen to this carbon instead, this positive charge will switch to this carbon, which has 3 carbons connected to it. So that will get me to a tertiary carbocation. Okay, so, and then reaction can proceed from there again. Take that hydrogen, this bonding electrons will go here, and then I'll have product. I'm sorry, this is so messy, but you get the point. Hopefully you can even kind of read that. But yeah, so we just went from a secondary to a tertiary carbocation again, and then the hydroxide took the adjacent hydrogen from that beta carbon, and we're going to take it from this carbon instead of this one because that will give us the more stable product, and these are E1 reactions, So we're always making the more stable product, okay? Everyone good with that now? Okay. So if you have any other questions, feel free to put them in the chat or email me or message me on GroupMe or anything. Or you can make a tutoring appointment with me. If there are not any other questions, then that's all I have. So thank you guys for coming, always.